in yesterday's lesson, we talked about perpendicular bisectors and angle bisectors. We're still talking about those bisectors today, but what we're going to learn are some special things that happen, special relationships that happen in different kinds of triangles when those angle bisectors and those perpendicular bisectors intersect one another. So I inadvertently wrote the same definition here that I had at the beginning of last lesson. So if you don't mind, just go ahead and write it again. A line, ray, or segment that's perpendicular to a side of the triangle at the midpoint of the side, as we know, is the perpendicular bisector. We talked a whole lot about those last time. We learned some theorems about the perpendicular bisectors and angle bisectors, but now we're going to talk about something different. All right, if we have three or more lines that intersect at the same point, we call them concurrent. Concurrent. You know, typically when you think of the word concurrent, you think of something that's going on at the same time. Well, when we are talking about concurrence in lines, all these lines are going to intersect at some point. All right, and if we want to name the point of intersection, we call it the point of concurrency. The point of concurrency of those concurrent lines, appropriately enough. All right, so all that means is if I've got three lines coming somewhere, they intersect at some point, that point is the point of concurrency. All right, now let's talk about the perpendicular bisectors of a triangle. Perpendicular bisectors, you know, are going to be the lines that are the perpendicular bisector of each side of the triangle, and where they intersect has a special name, and it's called the triangle circumcenter. In the next couple of lessons, you're going to have a lot of terminology to keep straight. So if you haven't made a single flashcard this year, you definitely must do it in this unit, because you will never, ever keep all this straight if you don't practice. Okay, so the circumcenter, point of concurrency of perpendicular bisectors. All right, we got a theorem, of course. It says the perpendicular bisectors of a triangle are concurrent at a point that is equidistant from the vertices of the triangle. So let's look at this triangle we got here. You see, we have the perpendicular bisector of AC right here. Got the perpendicular bisector of BC right here. Got the perpendicular bisector of AC right here. That point where they all come together is the circumcenter. There's the circumcenter. And what does this theorem tell us? It tells us that that circumcenter is equidistant from the vertices of the triangle. In other words, PA, I'm going to mark them as congruent. We know that means that their lengths are equal. PA is the same length as PB, is the same length as PC. So somehow you have got to remember that the circumcenter is equidistant from the vertices of the triangle. All right, now, and it doesn't matter what kind of triangle it is, acute, obtuse, right triangle, the circumcenter will always be equidistant. However, what you must remember is that depending on the kind of triangle you have, your circumcenter may be inside the triangle. If you got an acute triangle, if you have a right triangle, the circumcenter is going to be on the triangle. And if you have an obtuse triangle, your circumcenter is going to be outside the triangle. All right, it's still equidistant from the vertices of the triangle, but can be inside, outside, or on. Very important that you remember that. All right, let's see what else we're going to learn today. A bisector of an angle of a triangle. Oh, we've known this for a long time. Divides the angle into two congruent angles. We've known that for a long time. No harm in repeating it, writing it down one more time to refresh our memories. Okay, now, what about the point of concurrency of the angle bisectors of a triangle? That's called the triangle's incenter. So you got the circumcenter, that's the point of concurrency of the perpendicular bisectors. You've got the incenter, that's the point of concurrency of the angle bisectors. So, how about a little theorem? The bisectors of the angles of a triangle are concurrent at a point, and of course we know this point now is called the incenter. And there it is. There it is in this triangle. There's our incenter. And what do we know about the incenter? We know that it is equidistant left my line out there, equidistant from the sides of the triangle. All right, so if we draw a perpendicular, so remember when we talk about equidistant to the side of a triangle or an angle, we're talking about a perpendicular distance. So if we start at our incenter, draw a perpendicular to BA. All right, and we start at the incenter, draw a perpendicular to BC. From the incenter perpendicular to that last side of the triangle, AC, then we know that all of those perpendicular lengths are the same. So PD equals PF, which is equal to PE. So there you go. If we didn't have anything else to learn, you'd have enough just to keep that straight. The incenter from the circumcenter, and which one's equidistant to the vertices and which one's equidistant to the sides. A lot to keep straight. Please, please make flashcards and practice. Okay, now, you remember how the circumcenter could be inside, outside, or on the triangle? For any triangle and every triangle, the incenter will always be inside the triangle. It's always incenter. Think of this. Incenter will always be in. Incenter will always be inside. Okay, let's see what we got here. Probably some examples. Yep, a little practice. The perpendicular bisectors of PQR meet at point S. Let me just give you a little tip on how you can come to remember the different terminology. What I think would be good for you is whenever you're working a problem and they give you this, like the perpendicular bisectors of PQR meet at point S, immediately you should say to yourself, what is that point called? Perpendicular bisectors? It's called the circumcenter. Write that down. Every time you have a problem, stop and write down whether you've got a circumcenter problem or an incenter problem, because I hate to tell you, but there's some more terminology coming in future lessons. So stop right there, write down, okay, I'm talking about the circumcenter. What do I know about the circumcenter based on the theorem? Oh, I know that the circumcenter is equidistant from the vertices. So now, what are we going to do? We're going to find PS and QS. I'm going to highlight these. Here's PS. Here's QS. And what do I know? Well, I know that PS equals QS equals RS, right? That's what I know because of the theorem, so I don't really care about all this other stuff they've got going on here with 8 and 9.6. Doesn't matter. What I know is that all those lengths are the same, so that's 10 units. I don't have any units on there, so that's all I got to know. But you see, guys, if you don't remember the theorem, then you're going to get thrown off track by all these other numbers out here that don't really have anything to do with what you're trying to answer in your question. Got to know this. Got to memorize these relationships. Okay, now we've got the angle bisectors. What do we know about the point of concurrency of the angle bisectors? We know that's the incenter. I'm going to write it down until it's always at the forefront of my mind. Okay, what do I know about the incenter? I know it's equidistant from the sides, right? From the sides of the triangle. And of course those links have to be perpendicular, so I know that that, and that are the same because here's my incenter. So what am I trying to find? WY. Okay, well I know that WY equals WZ equals WX. I don't know what any of those are, but I do know that I can figure out what D is by setting WZ equal to WX. So I'm going to say 4D minus 1 equals 2D plus 7. 4D minus 2D is 2D. 7 plus 1 is 8. So D equals 4. So if I plug 4 in here, I get 15. So therefore, these are all 15 units long. Let's scroll back up. I forgot to point out something very special. Even though this unit is a little bit hard, a lot of things to memorize and remember, it is really there are some spectacular facts that you're going to learn. For instance, the incenter. The incenter will also be, not only is it the point of concurrency of the angle bisectors, but it is also the center of the circle. The center of a circle that has a radius of the length of the distance from the incenter to the side of the triangle. Okay, so and what we call this, when we have a circle that is inside, and this circle is tangent to this triangle at 3 points, right? 3 points of tangency. A circle that is inside of a triangle like that with 3 points of tangency, we call that circle inscribed. That circle is inscribed in the triangle. Sorry, I forgot to point that out to you. So while you're moaning and feeling bad about how difficult the concepts in this unit are, there are some really fascinating things that you're going to learn. So maybe try to look at it that way too. All right, what do we got next? Another example. In the diagram, the angle bisectors meet at point H. What does that mean point H is? That means point H is the incenter. And we know, therefore, that these are equidistant. H is equidistant from each of the sides. So I know that HN is congruent to HP and is congruent to HM. So let's see, what are we trying to do here? We're trying to find what all those are, which is really just one length. Okay, so what do we got here? I'm going to just look at this right triangle that I have right here. Got a right triangle. All right, I know what the hypotenuse is. I know what one of the legs measure is, so I can just use the Pythagorean Theorem, right? So I know that 25 squared equals x squared. We'll call this x right here. X squared plus 24 squared. So 25 squared minus 24 squared equals x squared. So let's see, if I take the square root of both sides, I'm going to get 25 squared is 625. 24 squared is 576, and that equals x since I took the square root of both sides. And that is the square root of 49, which equals 7. And x is HN, HP, and HM. All right. Let me know, of course, in class if you have any questions about any of these problems that we've done today. What I want you to do now is turn off the video and do some constructions. All right, I want you to construct the circumcenter. Do the circumcenters on this side. Do the incenters on this side. And I want you to see what you find out. These are right triangles right here, I should point out. So what you've got are acute triangles, right triangles, and obtuse triangles. And I want you to verify for me what I told you about. Remember what I told you? The incenter will always be inside. I want you to verify that over here. Every one of your incenters should be inside these triangles. And over here, the circumcenter here should be inside. This one should be inside. This one on the right triangle, do you remember where I told you it is? It's on. The incenter should be on. It'll be on the hypotenuse. I want you to tell me where particularly it is on the hypotenuse when you get finished. And this obtuse triangle, you remember, the circumcenter will be outside. So I want you to verify that with your constructions. I will check those tomorrow. All right. The next lesson coming up will be on medians and altitudes. I'll see you then.